Okay, this is the final exam from spring 2017, and it's the last one that I'm recording for now. I've done uh, every exam up to this point, so after this I get to fly home for Thanksgiving. That'll be nice. Okay, question one. Find the equation of the plane that contains this point, and is perpendicular to these two planes. Well, we know that the normal vector of the plane perpendicular to two other planes can be found by doing a cross product. So we can cross 2, 1, -2, our coefficients for the normal vector from this plane, with 1, 0, 3, which are our coefficients from the second plane. And computing this cross product, we will get 3 and 8 and -1. And if you want to on your own, you can plug the 0.211 in, and it will match the constant that we get for answer E. But since it's the only answer that has 3, 8, and -1 in it, that is our answer. Okay, let's compute this integral. It looks like we're going to be using polar coordinates for this. Let's take a look at what our region is. It looks like we're dealing with the upper semicircle of radius 3, like that. And then x is running between 0 and 3. So we're dealing with this region right here. So we can express that in terms of polar coordinates. R runs from 0 to 3, r dr, and theta runs from 0 to pi over 2. And then we have root 9 minus r squared in here. We can integrate this, but first realizing that we can just remove that and put a pi over 2 outside. We can integrate this and we will get pi over 2 times the quantity -1/3 9 minus r squared to the 3/2, evaluated on 0 to 3. And we see that when r is 3, this entire expression is going to be 0, and when r is 0, this is going to evaluate to -27 over 3. So overall, we get 27 pi over 6, which will evaluate down to 9 pi over 2. Let's express the area of the surface given by this graph over the triangular region with these vertices. So we have the vertices 1, 0, 1, 3, and 4, 3. There we go. And let's label these points. 1, 0, 1, 3, 4, 3. So we're dealing with this region here. We see that all of our answer choices are integrating dx, dy. So let's draw a line parallel to the x-axis and see where it first intersects and where it leaves our region. So it's going to enter our region at x equals 1, and it's going to leave our region on this line here. Well, this line is going to be y equals x minus 1, or just x equals y plus 1. So our lower bound on x should be 1, and our upper bound should be x equals y plus 1. So let's look for that in our answer choices. We see that in answer choice B and E, and nowhere else. And we know that for dy, we only want the minima and maxima, so the extreme values of y, and we see that y runs from 0 to 3. So E is our correct answer. And isn't this nice? We don't have to deal, and this is pretty common actually, we don't have to deal with anything in the integrand. But if you want to find this entire thing on your own, we know that all we would need to do is take the square root of the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared plus 1. Let's compute the volume of the solid inside the sphere of radius 5 that is outside the cylinder of radius 4. So there's a cool little trick for this. I've linked the Wikipedia article for it on the spreadsheet, and so essentially there's a way to do this without any actual calculus, because the shape that this thing is going to make is what is apparently called a napkin ring. So we're going to get, I'll draw a cross section over here. So we have, let's say we cut our sphere along the YZ plane here, and we're looking at our sphere, and we've got our cylinder cutting through it. We want the solid inside the sphere, outside the cylinder, so our cross section is going to look like this. And if you can kind of picture this, this cross section is going to wrap all the way around, and we kind of get what is apparently formally called a napkin ring. But this is okay because we can find the height of this ring, and we have a formula for the volume of a napkin ring, which is, let's see, pi h cubed over 6, where h is our height. So let's find this height, and we should be able to solve. So we know here that the radius of our circle is 5 units, so we can draw a radial line up to the intersection of the cylinder and the sphere, so that's going to be 5. And we also know that the radius of our cylinder is 4 units, and we know by the Pythagorean theorem and my very not to scale drawing that this side over here will have to be 3 units. So we see that we have 2 sets of this construction per height of our napkin ring, and so we can set up our volume as pi 6 cubed over 6, or just pi times 36. But, oh no, that's not one of our answer choices. Well, that's because they want this such that y is greater than or equal to 0. So all that's going to do is cut our sphere and our napkin ring in half. So we're just going to get the half napkin ring. I don't even know what that drawing is meant to be, but hopefully you can kind of see how this problem has a nice shortcut method to it. That said, if they had us integrate anything in the integrand for this question, if we were integrating like the double integral over s d, or like z ds over this region, then we would have a bigger problem on our hands, and we can't do this kind of shortcut. Okay, let f be a vector field and curly f be a scalar field. Which of the following expressions are meaningful? So we know that we can only take the curl of a vector field. So 1 does not work. We know that the gradient of a scalar field is a vector field, and we know that we can take the divergence of a vector field, so 2 is good. That said, we know that we have to take a cross product, that we can only take a cross product between 2 vectors, but the divergence of f will give us a scalar, so 3 does not work. And then finally, we can take the curl of the curl all we want, and there's nothing wrong with it because we will have a vector field in both instances. So 2 and 4 is our answer. Okay, let's evaluate the line integral over c of f dot dr, where c is the line segment from 1, 0 to 0, 2. And here is our vector field here. And they tell us it's a conservative vector field. So I'm going to use my kind of technique to find the potential function of this vector field. And we know that if we find this potential function f where f is, or the gradient of f is our vector field f, we can evaluate f on our endpoint and our start point, subtracting our start from our end, and we will get our answer. So in order to find this potential function, we have to take antiderivatives of these two components with respect to whatever component they are. So the partial derivative of y e to the xy is going to be e to the xy, and then moving on to the second component, we will get e to the xy plus sine y. And so we see we have overlap here. We only count this overlap once, and our final function, our potential function, is e to the xy plus sine y. So now, since we have p and q in terms of x and y, we can evaluate this. E to the xy plus sine y on, well, let's see, our ending value is q, so 0, 2, and our starting point is p, so 1, 0. This will give us 1 plus sine 2, and over here we will get 1 plus sine 0, which is just 0. So overall, our answer is sine 2. Let's use Green's theorem to evaluate this line integral here, where C is the triangle. Oh God, I'm sorry about that. I got I got up kind of early today. I'm wearing noise canceling headphones, but that still scared the crap out of me. Okay. Sorry about that. I will leave that in there. So we're dealing with the triangle with vertices 0, 0, 2, 2, and 2, 4. So we can draw these in there, and we can see that really we can define this as two lines. This is the line y equals x, and then we have the line y equals 2x up there. That'll come in handy in a bit. So we know that the line integral over the curve of p dx plus q dy by Green's theorem is equal to the double integral over the region R of the partial derivative of q with respect to x minus the partial derivative of p with respect to y dA. So we have our p and q. P is just going to be xy squared, and q is going to be 2x squared y. And so we can evaluate this. So the partial derivative of this guy with respect to x is going to be y squared, and the partial derivative of this with respect to y is going to be 2x. Oh, wait a second, I did that in the wrong order. There we go. Let's fix that. So the partial derivative of p with respect to y is going to be 2xy, and the partial derivative of q with respect to x is going to be 4xy. And we see up here that we're subtracting p from q, so our integral is going to become the integral over r of 2xy dA. And since we've already identified that there are two lines here defining y up here, let's do dy dx. We said that y was bounded on the bottom by the line y equals x and on the top by 2x. And then we see that our extreme values for x are 0 and 2. So now we can integrate. Let's see, xy squared on x and 2x is going to give 4x cubed, and over here we are going to get x cubed. And finally, the integral from 0 to 2 of 3x cubed dx is just going to be 3/4 x to the 4th on 0 to 2, which is 16 over 4 times 3, which is 12. Okay, for problem 8 and 9, f of x is this guy right here, and we are looking for, problem 8, we're looking for local extrema. So we know for this, we're going to need the second derivative test, which is going to involve a matrix made up of fxx, fxy, fyx, and fyy. If the discriminant of this is greater than 0, then we have two choices. If fxx is greater than 0, we have a min. If fxx is less than 0, we have a max. And if the discriminant is less than 0, we have a saddle point. And of course, if the discriminant is equal to 0, we don't know anything at all. Okay, so let's find fx, fy, and all of our other second order partial derivatives. So fx is going to be 6xy, and fy is going to be 3y squared minus 3 plus 3x squared. So we can make our matrix, but also we have to note that our local extrema will only exist where both of these guys are equal to 0. And we can get some hints from our answer choices. Every answer choice mentions 4 local extrema, and we see that in order for fx to be equal to 0, we would like for one of these values to be 0. So the 4 obvious candidate points are 1, 0, 0, 1, -1, 0, 0, -1. And we see that this will satisfy fx in every case because we'll always have one 0 term. And over here, it will satisfy fy in every case because one of these two will be 0 and the other one will work out to 3. So in every case, this will be 3 minus 3 equals 0. So here are our 4 points. Now we just need to set up our matrix. So fxx is going to be 6y, fxy is going to be 6x, fyx is going to be 6x, and fyy is going to be 6y. So 6y, 6y, 6x, 6x. And now all we have to do is plug these guys in and see what happens. So if we plug in 1, 0, we are going to get a saddle point because our discriminant will be less than 0. We'll get the matrix 0, 0, 1, 1, which will give us a discriminant of -1. So we have at least one saddle. Let's keep a running tally. 1 saddle. Then, okay, 0, 1, we're going to get the matrix 1, 1, 0, 0, which our discriminant will be 1, which is greater than 0, and fxx is greater than 0, so we have a min. Now for -1, -1, 0, we're going to get the matrix 0, 0, -1, -1, and this thing is still going to be a saddle point because our discriminant will be -1. So we got another saddle, and then finally, this last point, 0, -1, will give us -1, -1, 0, 0. Our discriminant is positive, it's 1, and fxx is less than 0, so we have a max. So 2 saddle, 1 min, 1 max, and we're done. Okay, the absolute minimum value m and the absolute maximum value m for f of x and y on this rectangular domain. Let's sketch this out to begin with. X runs from -2 to 2, and y runs from 0 to 2. So here's the domain we're dealing with, and we are looking for the absolute minimum and absolute maximum of this function here. So instead of doing any real math, this is actually a good opportunity to work on thinking through these kinds of problems like almost like logically, which is good practice for going back and checking your work, especially for Lagrange multiplier questions, etc. Uh, and so pretty much we uh, we have to look at our f of x, y up here and determine what we should do, whether we should maximize y, minimize y, or maximize y, or minimize x in order to get our maxima and minima. Well, if we want a maximum, let's see, if we plug in y equals 2, we're going to get 8 minus 6. Well, that's greater than 0, and that seems like the best we can do, because anything less than that is going to give us a net value of smaller than 2. Like we can try plugging in y equals 1. That's going to give us 1 minus 3, which is negative 2, which is less than 2. And so, I don't know, x can either be positive 2 or negative 2 in this case because it's squared, but we would still like x to be positive 2. So right now we're dealing with this 0.22 over here, and we see that this will be 3 times 4 times 2. So overall we have 2 plus 24, which is a max of 26. So our max seems like pretty obviously is going to be 26. Now for our min, let's see. Well, we can't have a negative y, and any y that we put in here is just going to make our function bigger. So our min is probably going to occur where y is equal to 0. And if y is equal to, oh, sorry. Yeah, sorry about, no, I'm wrong. See, it's kind of a process of thinking it through, and then the key is figuring out when you're going down the wrong path, because this will actually be minimized when y is equal to 1. What we saw earlier, when we plug y equals 1 in, we will get 1 minus 3, and then since we don't want to add anything to our function, we're looking for a minimum, we can set x equal to 0. And so this will give us a min of negative 2. And so D should be our answer. Okay, let's use some differentials to evaluate the total error in the surface area of a silo, where that area is given by 3 pi r squared plus 2 pi rh. We can do this by adding together the total maximum error produced by R and H with these maximum error bars that they give us. So this is going to be given so if we have an error function for R and an error function for H, that will give us our total error. So we can define these. Our error function for R is going to be AR delta R, where AR is the partial derivative of A with respect to R, evaluated at our height and radius that they have measured, and our delta R is our maximum error given here. And then finally, our EH is going to be AH delta H. So we can find these. AR is just our partial derivative of A with respect to R, which will be 6 pi R plus 2 pi H, whereas AH is going to be 2 pi R. So evaluating both of these at 20, so H equals 20 and R equals 8, we will get, let's see, 48 pi plus 40 pi, so 88 pi up here, and down here we will get 16 pi. And so from this we can find ER, which is going to be delta R, so 1/4 times AR, which is 88 pi, and then we can find our EH, which is 1/2 times 16 pi. So this evaluates to 8 pi, this evaluates to 22 pi, and our answer is, as we said up here, the summation of those, which is 30 pi. The equation xyz minus 2x ln y minus z squared equals 2 implicitly defines z as a function z of x and y near 3, 1, 1. Let's find the tangent plane to this function at 3, 1. So we know that this tangent plane, because everything's implicitly defined over here, is going to take the form z, zz, z naught, z minus z naught, plus zx, x minus x naught, plus zy, y minus y naught, and then that is going to be all equal to 0. So let's find these things. We need three partial derivatives, zz, zy, and zx. And let's see, zz is going to be xy minus 2z. Zy is going to be xz minus 2x over y. And zx is going to be yz minus 2 ln y. So now we know what x, y, and z values we're at. These are our x naught. Let's just write this out. Our x naught, y naught, and z naught of 3, 1, 1. So xy minus 2z is going to be 1. Xz, let's see, this will be 3 minus 6, so negative 3. And over here, we will get 1. Okay, so at this point, we have everything we need to set up our equation. And I'm going to take all this. I wrote a little bit big. I'm going to move it down because we need some good space over here. So this is going to all work out to 1 z minus 1 plus 1 x minus 3 plus negative 3 y minus 1, and all of that's equal to 0. So simplifying, we will get z minus 1 plus x minus 3 minus 3y plus 3. And we see that we can rearrange this to z plus x minus 3y equals 1. And z plus x minus 3y equals 1 is answer choice E. Let's let S be a parametrized surface given by R of u and v, where it's composed of x as a function of u and v, y as a function of u and v, and z is a function of u and v. So, and they are looking for the upward pointing normal to S at 1, 2. So we know that our normal of a parametrized surface like this is going to be given by Ru cross Rv, where Ru and Rv are the partial derivatives of R with respect to u or v. Additionally, we see that we want an upward pointing normal, so our z component should be positive, which immediately rules out A and E and C. So we're left with a 50-50 if we just realize that. So let's find Ru and Rv. Ru is going to be v, 2u, 1, and Rv is going to be u, negative 2v, 2. Okay, so we see that we're at the point u equals 1 and v equals 2, so we can replace these things in here. This is going to be equal to 2, 2, 1, and this guy is going to be equal to 1, negative 4, 2. So we should be able to take this cross product and get a vector that matches one of these guys. So we are going to get 8, negative 3, and negative 10. And we see that B is the upward pointing version of this vector. This would be because we have a negative z component, this would be our downward pointing counterpart. Okay, a surface S is the graph of z equals xy above the region D, and they tell us that if the surface integral of xy z ds is a double integral of g of xy dx dy, then they want to know what g of xy is. So essentially, all they're saying is turn this into a rectangular integral and tell us some things about it. So we see that up here, z is equal to xy, so we can go replace that. Now we have the double integral over s of x squared y squared ds. And we know that we can change this from a surface integral ds to a rectangular integral over d dx dy by replacing our ds with root zx squared plus zy squared plus 1, where zx in our case is y, where z is xy, and our zy is x. So this whole thing is going to be x squared plus y squared plus 1. So now we have the double integral over r of x squared y squared root x squared plus y squared plus 1 dx dy. And we see that if we take this thing and stick it in here, we will have the square root of x to the 6th y to the 4th plus x to the 4th y to the 6th plus x to the 4th y to the 4th. And that is answer choice C. Okay, if z is a function of x, y, and t, x is a function of u, v, and w, and that follows for y and t, we are looking for zv. So this is a multivariable chain rule. We know that we can find this by taking the partial derivative of z with respect to x and multiplying that by the partial derivative of x with respect to v, and then I'll write the rest of this out. Partial z, partial y, partial y, partial v, partial z, partial t, partial t, partial v. And all of this is going to give us our partial derivative overall. So let's find some of these things. Zx, zy, and zt are going to be pretty easy to find if z is x e to the ty. Well, zx is just going to be e to the ty. Zy is going to be x t e to the ty. And zt is going to be xy e to the ty. We are evaluating this at u is equal to -2, v is equal to 1, and w is equal to 2. So we can plug those values into x, y, and z to see what x, y, and z are equal to on this level of the question. So x is u squared plus v. That will give us x equals 5. Y is vw. That will give us y equals 2. And t is w squared u, which is going to give us, looks like -8. Yep, t equals -8. So over here we can go in and solve. Did I screw one of these things up? X is 4, 5. Y is 2. Okay, we should be good. I think we're okay. E to the ty is going to give us e to the -16. This guy right here is going to give -40 e to the -16. And this here is going to give us 10 e to the -16. So we have half of our answers. Now we just have to evaluate the rest. Let's see. And for that, we're going to need an xv, a yv, and a tv. Well, xv is going to be 1, yv is going to be w, and tv is going to be 0. So replacing this w with our value for w up here, which is 2, we have everything that we need. And so we see that our answer is going to be xv times zx, which will be e to the negative 16, and then we are subtracting 2 times 40 e to the negative 16, which is negative 79 e to the negative 16. That said, I don't think I should just be getting 79 here. If you've already figured out why, good on you. Let's see if we can figure this out. U is equal to negative 2, so x is equal to 5. Y is equal to y is equal to 0, right? I think. Yeah, okay. There we go. That's my mistake. Y is equal to 0. I hope you caught that before and you've been yelling at me ever since. This is going to be 1. This is going to be negative 40. And this is going to be 0. So, yes, here we go. We get our 1 minus 80, which is negative 79. And that's the thing with these questions. There's so much you have to compute and so many variables you have to deal with. It's very easy to miss something minor along the way. Okay, classic spherical integration problem. If you've done all these exams, you should pretty much be able to do this one in your sleep. So that said, let's go for record time on this one. We know that z in spherical coordinates is rho cosine phi, and we know that what's sitting in our integrand already is going to be rho squared sine phi. So overall, our integrand is rho cubed cosine phi sine phi, d rho, d phi, d theta. And we're looking for the solid between, let's see, rho is equal to 1 and rho is equal to 2 in the first octant. So these are going to run from 0 to pi over 2 and 0 to pi over 2. We're not dependent on theta, so this just becomes pi over 2 out here. Okay, so evaluating rho to the 4th over 4 on 1 to 2 is going to give us 4 and 1/4. So this is 15, I'm sorry, not 15 sixteenths. 16 over 4 minus 1 over 4, which is 15 over 4. So now we are left with the integral times 1/2 from 0 to pi over 2 of, 15 over 4 sine phi cosine phi d phi. We know that sine phi cosine phi can be replaced with sine 1/2 sine 2 phi, which we can integrate, and we will get 15 pi over 8 times the integral of negative 1, sorry, this thing, the quantity, negative 1/4 cosine 2 phi on 0 to pi over 2. This is going to give us, let's see, cosine of pi is going to be negative 1, so this is 1/4, and this is negative 1/4, and so overall in here we got 1/2, so 1/2 times 15 pi over 8 is 15, that's a terrible 8, 15 pi over 16. Let C be the curve parametrized by this thing. At what point does the tangent line to C at 2, 1, negative 3 intersect the YZ plane? So in order to find this, we have to find the t value for which this is true. And if we look up here, we can just equate our x components. Negative 2 equals 2t, t equals negative 1. So at t equals negative 1, we can find our r prime of t, and that will give us the slope of our tangent line. So r prime of t is just going to be 2t, 2 minus 2t, which when we evaluated at t is equal to -1, so r prime of -1 is 2, -2, 4, which is perfect because now we have a full parametrization for this tangent line. This will be -2, 1, -3, which is just a point on the line, plus t times 2, -2, 4. So every unit t, we know that we'll be moving this much. And we want to see where this intersects the yz plane. Well, that's for x is equal to 0, and x is equal to 0 when t is equal to 1, because -2 plus 1 times 2 is going to be 0. And so if t is equal to 1, we are going to get, as we said, 0, then -1, and 1. And we're done. Let's compute the arc length of this curve. Well, that's easy. We need r prime of t. That's going to be 2t, 1 over t. Now we need the sum of the square root of the sum of the squares of these things, which is going to be the square root of 4 plus 4t squared plus 1 over t squared, which we can factor down to 2t plus 1 over t squared. And these things cancel, so we're left with the integral from 1 to 2 of 2t plus 1 over t dt. That's going to be t squared, t squared plus ln t on 1 to 2, which is 4 plus ln 2, and this is 1 plus 0. So overall, we get 3 plus ln 2. Let's compute the surface integral over the surface S of x ds, where S is the triangular region with these vertices. Oh, whoops, we're in 3 dimensions. Where S is the triangular region with these vertices. X, y, z, we have, 1, 0, 0. We have 0, 2, 0, and we have 0, 4, 0. There we go. And so it looks like we are looking at this region in here, and we want the surface integral of this whole thing. So there's a little bit of a weird strategy I used to figure out the equations for this. We know that when x and y are 0, z is equal to 4. And then all we have to do is look at the slope of the lines in the z plane and the xy plane to figure out what those coefficients are. The slope of x with respect to z, if you look at it going this way, is -4, right? Because we go over 1 unit and down 4. So minus 4x, and then the same argument applies for y. We go over 2 units and down 4 units, so minus 2y. And there's our equation. And so we know that we can mess with this surface integral here with zx and zy, because we're going to need the square root of zx squared plus zy squared plus 1, and that will help us turn it into a rectangular integral. This is going to be -4, is going to be -2, so our square root becomes 16 plus 4 plus 1, or root 21. So now we have the double integral over r of x root 21. We don't want to forget there is an x sitting up here, dA. And so now we know that we're only looking at the kind of 2D projection of this shape, onto the xy plane. And so we can draw that out. We have our y-axis and our x-axis, and we know that our x-intercept is at 1, 0, and our y-intercept is at 0, 2. And so the lines that define our region here are going to be x equals 0, y equals 0, and y equals, well, let's see, it's going to be 2 minus 2x. So now we can take our r and dA away and turn this into dy dx, where x runs between 0 and 1, and y runs between 0 and 2 minus 2x. So I'm going to make a little bit more space here because I'm running out. This dy, well, we don't have any y's in this integrand, so we're just going to multiply this thing in. And I'm actually going to move our root 21 all the way out because I don't want to deal with it for now. So we're going to be left with root 21 times the integral from 0 to 1 of 2x minus 2x squared dx. This is going to be x squared minus 2/3 x cubed on 0 to 1, which is just going to be 1 minus 2/3, or just 1/3 times root 21, which is d. Okay, let's let S be the semi-ellipsoid z equals 2 root 1 minus x squared minus y squared, oriented so that the normal n is upward pointing. And we also have this function here. You can, surprisingly, if you're used to Stokes' theorem enough, which I'm definitely not, but I realized this over time, you can do this question without doing any math. So we know that Stokes' theorem helps us to find the curl, the total curl through that's passing through a surface, and we know that it's not dependent on what that surface actually is, because all we have to do is use some parametrized curve or path that runs that encloses that surface. So in our case, we can set z equal to 0 and find that surface, because we know that we're dealing with what they're calling it a semi-ellipsoid, and it's the positive semi-ellipsoid. So we're dealing with this kind of half potato looking thing, and we can just take the path z equals 0 where this thing ends. So that's going to be 0 equals root, whoops, 2, oh come on, 2 root 1 minus x squared minus y squared, which we can rearrange to be 1 equals x squared plus y squared, which is just our circle of radius 1, which we know very well how to parametrize. So going back to what I was saying about how we can do this without any math, we see that if we take our f of x, y, z, for z is equal to 0, we are going to get what is completely a radial vector in the xy plane. So we have our circle of radius 1, and it's defined by x squared and y squared, and so all our vector field is going to be doing is flowing out through this area here. So that's important to note, because it leads us to our answer. Our answer is 0. There is no curl, but we can see that through the math. So let's parametrize this circle here, which is our path that encloses this region. That's going to be x equals cosine t, y equals sine t, and then we need, so I really should have written it out as r of t, cosine t, sine t 0, right, because z is 0. Then we need an r prime of t. That's going to be negative sine t cosine t 0. And I should have prefaced this with, if you're not used to the Stokes theorem kind of method, whenever they tell you to evaluate curl f dot nds, what they kind of really mean is that it'll be easier to evaluate the line integral over c of f dot dr, which is, this is Stokes' theorem, that these two are equal. So now, finally, we need an f of r of t, which is going to be cosine squared t sine squared t, and 0. So setting z equal to 0 gets rid of all of this tangent crap in there, which is what would make taking a curl very difficult here. So f dot r prime of t, evaluated on 0 to 2 pi dt, is going to give us negative sine t cosine squared t plus cosine t sine squared t. And it's pretty quick to see that each one of these integrals, if we split this up down the middle into two integrals, that if we do u substitution, in this case, we'll be setting u to cosine t. In this case, we'll be setting u to sine t. We'll be able to get rid of this other term, but our bounds on our integral are going to be, in the case of cosine t, they're going to be 1, 1, and in the case of sine t, they're going to be 0, 0. And so we're integrating over no area, really. And so our answer is 0 for both of these. Okay, this is the last problem I have to do today. I hope that this recording isn't corrupted or something, because that would really suck, and I need to go to class. So let's let f of x, y, and z equal to this thing, and we're looking for the using the outward pointing normal on the surface S of the solid box. Those are the magic words. That means we can use the divergence theorem, and we are given the bounds of the box. So we know that the double integral of f over s ds is, by the divergence theorem, if we're in a solid area, is equal to the triple integral over whatever region E we're in of the divergence of f dv. So these problems can be very nice sometimes, where we get a constant for the divergence of f, and all we have to do is multiply by the total volume of our region. But in this case, it's not so, because the divergence of f is del dot f, which we can set up as partial x, partial y, partial z, dotted with x squared yz, xy squared z, xyz squared. And so doing this dot product, we will get 2xyz plus 2xyz plus 2xyz. And so now we can set up our final integral, which is going to be the triple integral dx, dy, dz, where x runs from 0 to 1, y runs from 0 to 2, and z runs from 0 to 2 of 6xyz. This is going to give us 3x squared yz evaluated on 0 to 1, which is just 3yz. Now we're taking the integral from 0 to 2 dy. This is 3 halves y squared z evaluated on 0 to 2, which is going to give us, let's see, 6z. And 6z integrated on 0 to 2 dz is going to be 3z squared on 0 to 2, which is 12. And that is that. Okay, thanks for tuning in.